In section 7.6, we're going to learn how to do or solve differential equations that involve piecewise continuous functions. So differential equations where you have some function showing up that changes from one function to the next as time goes by. Before we get into this unit step function that I have written here, let me just give you a few examples, some practical examples of where these piecewise functions may show up in applications. So one example, if you think back to earlier in the semester, when we were doing those mixing problems, where you had some kind of solution flowing into the tank, and then you mix it, and then it flows out of the tank. Suppose in these mixing problems that we had, suppose we had some kind of valve on this input that could change your flow rate into the tank. So maybe if we look at flow rate over time into the tank, then maybe you start out at, say, a flow rate of, I don't know, 6 liters per minute. But then at a certain time, you turn the valve. And at that time, all of a sudden, you start having a different flow rate. And then maybe at some point, you completely shut it off. And then after a while, maybe you go back up to your original flow rate. So the idea is this valve gives us this piecewise defined function where over different intervals, over different time intervals, you've got different things happening. All right, so this is an example where these piecewise defined functions could show up. Another example would be maybe if we want to talk about electrical engineering or electronics, a simple concept would be if you're dealing with electronics, what happens when you flip a switch, right? So let's say you start out doing one function, but then at a certain time, you flip the switch, and as soon as you flip that switch, something else starts happening. All right, so this again would be a piecewise defined function where you've got something happening for some interval of time, and then all of a sudden things switch and something different starts happening. So again, there's natural places where these piecewise defined functions can show up in applications. And if we wanted to solve these things, whatever differential equations are associated with these scenarios, using old techniques would be kind of messy because we'd actually have to solve several different equations. We'd have to figure out what's happening on this first interval and then use that information to figure out what's happening on this next interval. And so you actually end up solving several equations just to handle this one problem. So the nice thing about Laplace transforms is Laplace transforms work well with piecewise defined functions. And so we've got some nice properties using Laplace transforms that will allow us to solve these types of differential equations where we have piecewise defined functions showing up. And the Laplace transform allows us to handle those kind of all lumped together instead of doing several separate equations. All right, so that's kind of the setup or the motivation behind what we're doing in section 7.6. Now let me get to kind of a few basic definitions that we need in order to use our Laplace transforms. All right, so the very first definition is this unit step function. The unit step function is something we'll use quite a bit in this section. It's a pretty simple function where it's 0 for all time less than 0, and then as soon as you get to time 0, from then on, it bumps up to 1. So you can think of this as like off and on. It's off for all time less than 0, and then all of a sudden at time 0 it switches to on. Graphically, what this would look like is, if this is our t-axis, for t less than 0, our function is always 0. But then at 0, we switch to a y value of 1, and then it's just 1 from then on. Okay, so there's our unit step function. And something else we may look at is we can shift this unit step function around. If we think of just basic transformations of functions, if I want to do u of t minus a, when I subtract some number inside my function notation, that means I'm shifting left or right. If a is a positive number like 3, I'm doing t minus 3, then I'm shifting right 3 units. If it's a negative number, so I'm doing t minus, say, negative 3, that'd be t plus 3, then I'd be shifting left 3 units, all right? So this lets us shift our unit step function left or right. So basically what this does is it's going to be 0 for t less than a, whatever a was, and then I'll switch to 1 whenever t is greater than a. Okay, so graphically what that would look like, again, if you've got your t-axis, wherever a is, wherever a is, it's not necessarily 0 anymore. Wherever a is, that's where you switch to flip on, turn on the function. It switches from being 0 to 1. All right, so that's the unit step function, and then we can shift the unit step function left or right as needed. The next type of function we'll want to look at is called the rectangular window function. And you'll notice in the book, when they define this, they say that this function has several different names. Sometimes it's called the square pulse function or the boxcar function. In your engineering classes, I guess it just kind of depends on who your professor is, what they call it. But we'll just call it the rectangular window function. And the way this is defined is, so first of all, this right here, this is a capital pi. So pi of t is our rectangular function. And then we've got this subscript a comma b. So this is capital pi and then a subscript a comma b, and then just regular function notation, pi of t. So the way this rectangular window function is defined is we've got these, we define it in terms of these unit step functions. I've got one that's shifted a units, another one that's shifted b units. And here let's assume that a is less than b. All right, so let's think about what this would look like if a is less than b. This function here, this first one, u of t minus a, if we think about what that looks like at a, is when it switches on, right? From there forward, it's 1. Okay. This other function, u of t minus b, it's shifted over b units. So it's shifted further to the right than this first one was because b is bigger than a. So what that one would look like would be it's 0 up until b. And then all of a sudden at b, it switches on. And then from then on, it's 1. Okay, so now let's think about what's happening if we subtract these two functions from each other. If I do u of t minus a minus u of t minus b, the second function is always 0. So up until this point b, I'm not subtracting anything. But then all of a sudden at b, this function is 1, And this first function is also 1. So if I'm doing 1 minus 1, when I subtract them, I'm going to get 0. So what the graph of this will look like is between A and B, your function will be at 1. But then everywhere else, it's 0. Okay? So everywhere else, it's 0. So this just gives you a little line segment between A and B. And everywhere else, you just don't have anything. So another way we could write this, if we wanted to write this using function notation, I would say something like this. It is 0 if t is less than a. It's 1 for any time between a and b. And then it goes back to 0 for any t values bigger than b. All right, so this is how we can describe it using piecewise function notation. Now let's think about how this can be useful for us. Suppose I have some other piecewise defined function, and I want to describe it in terms of these unit step functions. So the goal here is, if I've got this piecewise defined function where I'm doing something for a while, and then maybe at some point I switch and something else starts happening, and then here I switch again and something else starts happening. What I can do is I can look at these in terms of my windows. Let's say that this happens at times 1 and 2. And I'll call these pieces, I'll just call these F1, F2, and F3. If I want this F1 piece to show up, what I can do is I can take this F1 piece and multiply it by this rectangular window function between 0 and 1. All right, so if I do F1 times my rectangular window function between 0 and 1, this rectangular window function is just 1 between 0 and 1, so then I've got F times this thing that's 1 between 0 and 1, and then it's 0 everywhere else. So anywhere outside of this interval between 0 and 1, this isn't doing anything, it's 0. For this next piece, if I want that to show up, I can do F2 times my rectangular window function between 1 and 2. So I can do F2 times pi 1, 2. If I want this other piece, if this goes on forever, then I don't need the rectangular window function. I can just use my regular unit step function, because I don't need to drop back down to 0 ever. It's just going to keep using this last function, F3. So maybe I could do something like F3 times u of t minus 2, because I'm shifting to the right 2 units. All right, so if I look at these individually, this right here would just give me this piece and nothing else. It's 0 everywhere else. This right here would give me this piece and then nothing else, because the rectangular window function is 0 outside of this interval. And then this right here, it's 0 all the way up until 2, and then at 2 it switches to 1, but then I'm doing 1 times my function, so now I've got my function over this interval. All right, so then if I add these together, then I've got all 3 pieces. Because here, if I do this plus this, this is 0 everywhere outside of 0, 1, so it's not really affecting anything that's happening to this one. This one is 0 outside of this interval from 1 to 2. So when I add these together, it's not really doing anything to the other 2 pieces. All right, so if I add these together, then I get all my pieces combined. Let me show you this with a more specific example. to finish out this video. All right, so we've got this piecewise defined function. From times 0 to 1, we've got this function t squared. From 1 to 4, we've got a constant function 3. And then for t bigger than 4, we've got the function t. Okay, you can kind of imagine what this might look like. We don't have to graph this in order to answer this, but let me just give you a picture. Between 0 and 1, we've got the function y equals t squared. So that's just a parabola. So we've got this parabola shape. Between 1 and 4, you've got this straight line. It's constantly 3 between 1 and 4. So here, it's like we flip that switch, and all of a sudden, we go up and we're just constantly 3 for the next few seconds. And then at 4, we flip the switch again, and something else starts happening. We just use the function y equals t. So it starts at 4, 4, then 5, 5. So it's just that diagonal line. So it'd come up here to 4, 4, and then we'll just go on like this. All right, so this is our piecewise defined function. And again, you can think of all kinds of scenarios where something like this might show up. Like we talked about, maybe at time 1, you turn that valve to change the flow rate. And then at time 4, you turn that valve again. In terms of electronics, again, you just think of it as flipping a switch. At time 1, you flip a switch and something different starts happening. At time 4, you flip the switch and something different starts happening. So how do we write these in terms of window and step functions? So based on what we saw a second ago, we can kind of guess, and you may want to pause the video here and see if you can write this down. So yeah, go ahead and pause the video, see if you can write this in terms of window and step functions based on what we've talked about, and then press play to see how you did. So f of t, what we should have here is we've got 3 different pieces. So first, I'm going to have my window from 0 to 1. And on that window, I've got this t squared function showing up. So I've got t squared times that window function between 0 and 1. Plus, and remember, since this is 0 everywhere outside of this interval, then adding something to it won't affect anything that happens on those other intervals. Between 1 and 4, we've got 3. So we've got 3 times our window function, which is usually 1, but if I multiply by 3, then it's going to go up to 3. So window function from 1 to 4. And then finally here, we don't need a window function because it doesn't stop and go back down to 0 like a window function would. It just keeps doing this forever from 4 on to infinity. So we just need a unit step function for this last piece. So I'll do t times my unit step function, but I need to shift that unit step function to the right 4 units. So t times my unit step function shifted to the right, t minus 4. Okay. So this is in terms of window functions and step functions. I could write it strictly in terms of step functions, right? We don't technically even need these window functions. We can write it completely in terms of unit step functions. All right, so let me show you how that would look. So suppose this question said to write this not in terms of window and step functions, just write it in terms of step functions. How would that look? Well, how do I write pi of 0, 1 in terms of unit functions? If you go back to the previous page, we've got a and b. I've got u of t minus a minus u of t minus b. So if this is 0 and 1, I'd have u of t minus 0, that's just u of t, minus u of t minus 1. All right, so let's write that down. U of t minus 0, I don't need to write the minus 0, minus u of t minus 1. This is the same thing as this rectangular window function from 0 to 1. Then we do the same thing here. For the second one, 3 times. I've got my unit step function from 1 to 4. So I need to do it starting at 1, u of t minus 1. And then subtract it back off once we get 4, so u of t minus 4. And then we still have this that's already written in terms of a unit step function, so plus t times u of t minus 4. Now, I suppose we could clean this up a little bit because we've got a u of t minus 1 showing up in a couple of different places. We've got a u of t minus 4 showing up in a couple of different places. So let's go ahead and distribute everything out and collect things together a little bit. All right, so let's see, what does this look like? I've got t squared times u of t. And then I would have minus t squared times u of t minus 1. Then I also have a plus 3 times u of t minus 1. So I could write that as 3 minus t squared times u of t minus 1. All right, I've got 3 here and then a minus t squared here. So 3 minus t squared. And then what else do I have? I've got a minus 3 times u of t minus 4 and a plus t u of t minus 4. All right, so I've got positive t and a negative 3. So I'll write this as t minus 3 times u of t minus 4. So that just kind of cleans things up a little bit to get these individual pieces collected together. All right, so now we've got this written completely in terms of unit step functions without even using the rectangular windows. All right, now what you'll see in the next video is how we can use Laplace transforms with these unit step functions. Again, the whole point of all this is that Laplace transforms work nicely with these unit step functions. And so that's what we'll see in the next video.